How do we take partial sums of an arithmetic sequence? So first, remember what a partial sum is. So a partial sum is we're adding up some number of things, starting somewhere, ending somewhere else. It's not infinite. And an arithmetic sequence is defined by repeated addition. It has an explicit formula where you're taking your common difference and multiplying by n minus 1 and adding that to the original term to find a new term. The recursive formulas take the previous term and add the common difference. You should be able to recognize it in a list as well by having repeated addition. For example, this is an arithmetic sequence where the common difference is 4. So, according to legend, Gauss, a famous mathematician and physicist, was given this problem: find the sum of the first 100 positive numbers. As busy work by a substitute. And he figured out this way of doing it very quickly. And we're gonna take that method and apply it in many scenarios. So what he said was, well, let me take another copy of this. If I double it, if I call this S, 2 times that will be the same thing as 1 plus 100. 2 plus 99, 3 plus 98, and essentially listed out all of these up through 100, but he didn't bother writing it out. Just realized that, well, no matter which version we're adding here, this is 101, this is 101, this is 101. So this is 101 plus 101 all the way up through 101. And how many copies of this are there? Well, it's 100 times 101. So in other words, S equals 100 times 101 divided by 2, because we multiplied by 2 in the beginning. And that's 5,050. So we didn't have to bother typing all of those numbers into a calculator or adding them up in a list. That's the sum. And we're going to use this idea and apply it to a bunch of other things. So in general, this is the type of problem that we're going to be working on. Something starting with a starting value. So 4 is our starting value, and our summation is from 1 to 7. So this will be the number of terms in this case. Just be careful that it's 7 minus 1 plus 1. So if this doesn't start with a 1, you have to be careful. 3 is our common difference. And this is how we would write it out if we were doing it the long way, the way that we already described it. If this were a hard sequenced, this would definitely be how we would do it. But arithmetic sequences, as Gauss showed, have a better way. So he took this and drew it out into a diagram where, I don't think he actually drew it, but we can draw this into a diagram where we have 4. This first row is 4. The next row is 7. The next row is 10, 13. So every row we're adding another 3, and that's what that common difference represents. So if we take that common difference, here the total area of this shape represents the sum of those pieces. Now this is 7 by 22, but there are clearly pieces missing. The big idea was if we take a copy of this and essentially do the same thing that Gauss did of adding the other number in the list to it. So here, this is equal to 2 times the sum, and that's 7. 7 was, now we have a rectangle, which is really easy to find the area of. This is a 7 by 26. So S is 7 times 13. And this 7 times 4 plus 22 divided by 2 gives us our value much faster than having to write it out, especially if we make these numbers bigger. If I make this true for any random sequence going from 1 to n that's arithmetic, well, then this red piece refers to the starting value. These are blue pieces are all the common differences. The final value is this a sub n, and the total number of terms being added is the n. So I'm going to take a copy of that, turn it around, and as you see it line up, we get a rectangle. One side of the rectangle is n. The other side of the rectangle is a sub n plus a sub 1. And then because we doubled the total area, we have to divide by 2 to correct that. So here is going to be our formula. The sum of an arithmetic sequence from a sub 1 to a sub n is given by this sum. So we take the number of terms, so that's what the n represents, the number of terms, divide it by 2, and then add up the first term in the sequence and the last term that we're adding. If you look at the specific case where we're looking at the sum of the first n integers, so we're adding 1, 2, 3, 4 all the way up to 78 or some number n, it's n over 2. That's still there. That's the n over 2. And then the first number is 1. A sub 1 is 1 here. And a sub n is n here. So then we have n plus 1. And that gives us our formula. Let's find the... Ooh, that's an error. Let's find these sums. This is supposed to be a 79. So the first term... So first we figure out how many terms there are. 1, 2, 3, 4, 5, 6. And then we are adding the first term and the last term. So now we have 3 times 113, which gives us 339. Much faster than adding those all up. These, we recognize that it's arithmetic. There are 6 terms. We add the first term and the last term. 3 times 69, which is 207. Here, there are 30 terms. The first term, when m equals 1, we get 1 minus 6 times 1, which is 1 minus 6, or negative 5. So that's our first term. And then our last term is when m equals 30. 1 minus 180, so negative 179. Add those up, negative 184, and now we can do 15 times 184, which gives us negative 2,760. Certainly much better than adding 30 numbers together. Here there are 7 terms. And the first term is going to be 10 minus 7. The last term is going to be 70 minus 7. We get 66. So this is 7 times 33, which is 231. Yes, 231. Almost done. Let's find these sums. Well, here we're going from 6 to 55, and there are 8 terms. So we have 8 over 2 times 6 plus 55. This is the easiest when we are given what the first term is and what the last term is. 244. Here we have 12 terms. The first term is 16. The last term is 93. So we have 6 times 109. So 654. Lastly, and this is a little trickier, we're given the first term, we're given the number of terms, but we need to find the last term first. So what is a sub 50? This is where our explicit formula comes back in. It says that it's the first term plus our common difference times n minus 1. So in this case, it's 1 plus our common difference times n minus 1. 1 plus 147, so 148. And now we can use that in our formula. We have 50 terms. We add the first term and the last term. So we have 25 times 149. That's not easy to do in your head. 3,725. Here, same idea. The 45th term of this sequence that starts with 5 and has a common difference of 2 is 5 plus the common difference times 44, 45 minus 1. So we have 5 plus 88, or 93. So we have 45 over 2 times our first term plus our last term. 45 over 2 times 98. So this is 45 times 49. And 45 times 49 is 2,205.